So going forward from the energy that makes the things run, we go into more the internet aspects, which tightly depend on the topic of security. Hannes Tschofenig is working at the University of Applied Science in Bonn-Rhein-Sieg. And I've had the pleasure of working with him a lot in the context of the IETF, a lot on IoT security. That was more about, like, say, pre-quantum security, I'd say. And now he'll tell us a bit about how post-quantum security, post-quantum cryptography will affect the IoT. Welcome, Hannes.
Thank you, Christian. Thank you, everyone. Thanks for inviting me and for organizing the whole event. We've already today, like for those who attended the tutorial earlier today, we've seen a range of different IoT devices, and many had shown on the screen, small flash size, small RAM size, and really sort of minimalistic, that's why constrained IoT device characteristics. And as we will see later on, I think that's going to change a little bit. So maybe not as constrained as we would like. I'm going to skip all the sort of like history timelines that governments have on post-quantum crypto transition. I'm also not going to give a tutorial on these algorithms and quantum computers and so on. All interesting stuff, but not enough time. What I would like to do is give you a little bit of journey through the starting point here around 2015, when NIST put the call forward to work on new algorithms, cryptographic algorithms, to replace the traditional crypto mechanisms that we all like to use, RSA and elliptic curve cryptography. And at that time, barely anyone really cared much. Of course, some mathematicians who put forward the proposals, they really cared, but the rest of the industry was really silent. But that quickly then changed over the years, and now we, as we will also see later, we have so many activities going on. It's amazing. And a couple of years later, I gave a short presentation at the IETF, sort of claiming that we have a little bit an issue here. There's a mismatch between what we considered constrained IoT devices and what these algorithms actually required us to do, like also not just the devices, but also the radio technologies, which I called "Will Post-Quantum Crypto Make Constrained IoT Devices and Network Obsolete?" And I think the title says it all. And also at that time, many of us, even people in the room, were really busy optimizing every last byte out of the protocols. Like we optimized like everything. And just a few names there we worked on with many working groups were set up in standards organization, and many people, including people in the room, contributed to that development and contributed code into RIOT. And I believe the motivation really came from this famous RFC 7228 terminology for constrained node networks, which proposed different categories of devices and made the argument that the improvements will not be in sort of flash increase and RAM improvements, but instead will be on energy efficiency, which fits nicely into the talk we just had. And so those were the classes, and many of the devices you've seen in the tutorial sort of are roughly in the class 1 category. So obviously optimizing for those internet protocols, security protocols, optimizing for those was really a challenge. And at that time, the processors we had available were something like Cortex-M3, M4, not really high performance processors, of course. So in a nutshell, the situation looked pretty grim back at that time. And at just a different perspective outside mine at that time, Ericsson made a contribution to NIST, making 3 bold statements, which I believe this is John Madsen's work that I'm sort of copying and pasting here. He's saying the current NIST PQC candidates, which by now are finalized now, I have some links later on for you, he says candidates are not usable in many constrained radio networks. He says NIST should acknowledge that these algorithms is a major unsolved problem for these radio networks. And also that NIST should acknowledge the use of elliptic curve cryptography will still be allowed until and so on. And of course, NIST did not acknowledge and moved on with the work. But of course, also links in the slides to later talks from John. So he changed his mind. Business models also changed, and so the constrained IoT devices were probably less important for Ericsson. So what threats do we? Well, why do we? Well, the community in general worries so much about all of this is there are two types of threats that surface with the possibility of having a cryptographically relevant quantum computer. Namely, the first one is the harvest now decrypt later attack, and it's quite simple. You have typically state-sponsored attackers who collect all the traffic, store it, and then once they have a capable computer, they will then decrypt everything and will obviously then get your secret. And then that obviously poses some constraints on the timelines because you need to do something now because you never know when these quantum computers, these capable quantum computers will arrive. The other attack, obviously more devastating, is one where the attacker is able to break the authentication and the integrity. So he can basically, like a CA, he would then be able to issue new certificates and would, for example, with firmware updates, he could just create its own firmware image and distribute that, and this would be recognized as truly genuine. Depending on where you are with your preferences, you favor one attack more than the other. Today, on the sort of web-minded people, they have a strong favor for or preference or priority for the harvest now, decrypt later attack. That's why we see in the browsers already key encapsulation mechanisms to combine them with post-quantum or combine post-quantum with traditional algorithms already today in your browser, in like Chrome browser and Firefox and many others. For IoT, the situation, I think, is a little bit different because if you look at, for example, operational technologies like industrial IoT networks, confidentiality protection is not the highest priority. It's actually more, the availability is more important. So you may question some of those priorities, and of course you need to think about your own threat model, or like, is it going to help an attacker if they find out in 5 years that you transmitted some temperature data from today? Probably not, but it depends on your application. But on the authentication weakness, that's obviously a challenge because, as we all know, secure boot and the associated firmware update mechanism is really is core to the security of the IoT device, because if you cannot protect the sort of the unchangeable parts over a long period of time, you end up having problems. So if you as a company, if you need to do something now, you need to make sure that you can later update the device to, for example, switch out one algorithm against the other one. But if you have no foundation to base it on, then you are clearly in trouble. And that's why some of you, Kuhn and others, Emmanuel, have worked on firmware update mechanisms. And at that time, the most popular mechanism was a few years ago only. It was HSS LMS. It's a hash-based signature mechanism, fairly old, very conservative. But it was seen as the go-to technology back then, of course. And that's why it's mandatory to implement feature. And here's just to give you a little bit of data. This is from a paper that Kuhn and Emmanuel worked on. You see signature size of HSS LMS is like, that's the upper table, is with more than 4,000 bytes, is not great, to put it mildly. compared to like 64 bytes with traditional cryptography. So that's not good, but if you use it for firmware updates are not small anyway, so the relationship is probably not such a big deal for many devices and many networks. Also, as you can see, the performance, it depends. So the performance is actually pretty good, like compared to for hash-based signatures. And the important thing here is for firmware updates, you only need the verification part unless you do encryption, and then you have to use different mechanisms anyway. So they are the performance, and that's also typical for these new, or in general for these cryptographic algorithms. They all have different trade-offs. Some have larger key sizes, some have larger signature sizes, some have better performance, and so on. So it varies quite a bit. So that was a few years ago when we worked on these firmware update mechanisms, because we recognized that that's really a core foundational technology that we need to get right. And it's being finalized as we speak. If you look at the NIST website, you see a lot of acronyms. And this is just a slide in case you haven't seen those acronyms. So NIST published a few specifications. These FIPS 203, 204, 205 was sort of the initial bunch of cryptographic algorithms that were released. And another one, Falcon, is yet to be published very soon, expected. It's a backup algorithm. And again, a backup algorithm which hasn't been published yet is this HQC. So you have a range of different algorithms, and there are more in the pipeline, which of course is a good thing that there's some choice, but it also means that there's time to implement all of this. There will be different trade-offs. So you need to figure out for different applications what fits best, what implementation works best, and so on. And this is not the end. Unfortunately, sometime into the work, the community realized that switching, this is not just switching like before from one algorithm to another one. We did that. Many people switch from RSA to ECC. It's of course an effort, but here we talk about we switch to new algorithms because we don't know how long the old algorithms, the traditional ones, will be secure. But we switch to algorithms which we don't know whether they are secure either, because some of them are very new, and it takes a lot of time to analyze and to sort of correctly implement, etc., all these algorithms. So what the community came up with is a hybrid approach where we actually combine the traditional algorithm with the new one, which is a good approach, in my opinion. But of course, it also has a disadvantage, namely, you now have to deal with both. You have the implementations of both. You have the keys of both, and the key change and everything. You basically double everything. But that seems to be the approach that is going on now. And as we will see later, this work is actually lagging behind, because I think the community just only realized later that this is a thing. And actually, here's an example. Like, this slide is very overloaded intentionally, because it just for a very small fraction of IETF activities, standards activities, it shows you there's a ton of work going on. And some of it is still at a somewhat early stage, individual contributions not yet officially worked on. And it basically cuts through the whole standards organization, because you have crypto everywhere in all these protocols, which you now need to replace, and you need to take the nuances of different protocols into account. So it's a lot of engineering and research work to actually get all of this done. And here's only 3 examples of 3 different areas. The DLS working group, obviously quite important because many people use DLS. There's a lot of building blocks come from X509 certificates in the LAMPS working group, or what we prefer most is the COSI, the compressed version, and the Jose group, which has its own sort of track of activities like pure post-quantum crypto work or the hybrid work. So this, and the last one is an example for hybrid double key encryption, which also gained some popularity recently with, because of its privacy features. And you can see the full list. This was extracted from that GitHub repository below. There's a gigantic amount of work, but it's not just the specification work, but someone also has to implement all of this and test it. So it's a lot for the community to look into. I see the time is ticking, so I will focus on a few selected points and leave the other links in there. So the new algorithms, the ones that are already published by NIST, you can see that the key sizes, and that's why I color-coded the box below, you see the traditional algorithms, very short key sizes and signature sizes in bytes. And if you go above, this is the lithium MLDSA with a specific strength. The key sizes are just way, way larger, which of course means like storage, RAM. It means flash size because you have to, some of the keys have to be stored persistently. And you also have to think about like the data that goes over the wire for some of the radio technology like LoRaWAN, Sigfox and all that. So it's, and some of the key size or signature size are even larger for these hash-based signatures. This is the SLH-DSA. So it is a challenge. So I skip over those slides, RAM requirements and these performance measurements. And a word on the optimization. So in the past, we worked on different optimizations, and there's a lot of trade-offs that can be made depending on what your environment is. There's flash size, RAM, CPU speed, there's energy efficiency, and other properties that and security level. And you can trade them off depending on what you want. You can shift, you can have better performance, but then you need more flash and more RAM, or vice versa, and so on. So there's a lot of sort of room to optimize for specific applications, which, as some of the references here show, people do. So it depends a little bit. But the bad news is you can't optimize in all directions, sadly enough. So we had those published, these specifications published by NIST, and good so far. But, and this is the somewhat surprising aspect to all of this is, while it looked pretty grim, the situation totally changed. Because then suddenly AI came along. It's weird to say that, but silicon vendors in no time, and basically unheard of speed, cranked out processors and managed to change the game entirely. And I'll show you, I've used the NXP processor in a lab on Edge AI. And these are the sort of like 3 examples of processors. And if you look carefully, you will see, apart from modern processors, you will see RAM and flash sizes that are just totally out of any proportion in constrained IoT devices. But this is what is being offered here, because everyone wants to develop IoT products. I wanted to use the SDM board, but it was sold out for months because everyone wants these processors. And so in the SDM series, it's a flashless device. You can connect some high-speed memory, but the others like flash size 2 megabytes, RAM megabytes, and or half a megabyte, like it's crazy numbers. And obviously we need those numbers while the chip designers focused on AI, but we actually need these numbers for the post-quantum crypto to easily do all the computations, which is a good thing. And if you think about, like, for example, a typical boot process, if you have secure boot, none of the applications are running. So the MCU, the processor, has all the memory and everything on it for itself. So it can also use that, and we're not running multiple applications in parallel either. And often these processors, like the Renaissance, it's a multi-core processor, also not uncommon. Also the NXP dual core. So you can run the security on one and the application on the other one. And really high processing speed because it uses new instructions. And if you think back about the processors that were common back in the good old days, M4 and so on, these processors have, and that's where the benchmarks are made, but nowadays people use those processors. Another interesting development, there is a separate talk about this tomorrow, is the Cyber Resilience Act from the European Commission, which places new constraints on companies selling digital devices, which basically everyone sells digital devices nowadays. And the one facet which I find interesting here is that there's a ask for a mandate to manufacturers that they actually make up their mind about how long they think their devices will be supported, which is really important because manufacturers now need to think like, how do I want to go forward with the devices and how do I dimension the hardware? Because it was not uncommon that people buy hardware and then only later figure out what they put on that device. And then to realize, oh, half of the security doesn't fit. But you have to leave, and that's what I say here, you have to leave a lot of headroom for the future because you don't know how the algorithm situation will evolve in the future. You may need to be prepared to swap out one thing. You may need to store more keys. You need to have sufficient space, not just for your AI applications, but then also for your keys. So it's good that these processors come with lots of memory. And you need to think about this crypto agility and maybe reduce the expected product lifetime to something that is a little bit reasonable, because who knows what will be sort of threat-wise in existence or algorithm-wise in 10 years. Like even with the changes we've seen in 5 years and also how the companies change their mind even in 2 years, how will you plan for 10, 20-year industry product lifetimes? I think it's completely impossible. And that's my final slide. Sorry for rushing through a little bit. There are a couple of suggestions from my side is like, I obviously like what vendors are doing, chip vendors, sort of raising up the bar to a level that I wasn't expecting, surprised me, honestly. For some of these low power radio technologies, I think we have to acknowledge that they were not built for these type of use cases. They were not built for post-quantum crypto. They were not built for many of those transfer sizes. But they can also still keep going with the symmetric keys as they have been doing in the past. So that's good. For developers, we obviously face the need to update a lot of the code. And we should have done that already anyway. Like I recently surveyed with a student some of the COSI libraries, and not all of them are great, to be honest. Unfortunately, some people just abandon their libraries or barely look at them. And so they are full of security holes. So that would be a good opportunity to actually go through, as you're adding PQC, fix the other thing as well. And SDOs, they obviously still have to get the work done and do intro testing, and then hopefully finalize the firmware update specifications. And I'm looking at Kuhn in the back here. But and thank you all. I hope I could give you some ideas for this post-quantum crypto, and please help us to finish that work, progress that work, and make crypto a better place.
Thank you. I think we still have time for like 1 or 2 questions.
Yeah, thank you for the presentation. Just thoughts. I wouldn't care too much about the signature side of the wire if I just do the exchange once for a symmetric key and then switch to plain old trusted symmetric crypto and continue on. Well, you still need the algorithm on the device, of course, but you know, transfer the signature, the huge signature every time.
Yeah, and that's what we've been doing in some of the protocols, like amortize the cost for the initial exchange over longer duration. There will be a talk tomorrow about the connection ID in DTLS to avoid rerunning the TLS handshake, so you can actually run it for a very long time. So there are good ways to deal with those. Yeah, definitely.
Did you actually get hands on those devices finally and made some testing on them?
Yeah, I had the NXP board, but I used it for AI purposes, edge AI. So the use cases there is like predictive maintenance. It's not the ChatGPT type of use, obviously, because even a Raspberry Pi has problems there. But so there are many industrial applications where you want to sort of not contact the cloud for everything, but actually do some of the preliminary computation, HML, on the device and have a decent performance, and then send off the load. So we worked on those and tried different algorithms, machine. So there are lots of different artificial neural network use cases in that space. I didn't use the crypto algorithms there yet, but other companies did. So, for example, Wolf SSL, they played around with some of those higher imports. So it's definitely like what would be really interesting is actually to optimize the algorithms for use on those devices. So in the Wolf SSL case, they optimized it for Intel CPUs, which is obviously not so helpful for us. But even if you optimize it like the one of the referenced projects, was the EU-funded projects to do the benchmarks on a Cortex M4. So that's obviously was good at that time, but it would be good to actually use modern ISAs and optimize the assembly instruction for those type of architectures, because they have lots of new features which weren't available back in 2010, clearly.
Seeing no more questions, thanks again, Hannes.
Thank you.